I mean, just a quick summary of what we discussed yesterday, and then we will take it forward today. And later in this session, we will have a hands-on practical on implementation of CNN for image classification. Before that, I'll give you overview of convolutional neural network. And yesterday it was a long session, so I thought of concluding it little early. I mean, 15-20 minutes early, because I thought let's discuss convolutional neural network today, and then in continuation we can have the practical session. So now, yesterday we discuss the historical perspective of neural networks, starting from maculopate neuron, perceptron, then sigmoid neuron. We also talked about the learning algorithm, gradient descent algorithm. We talked about backpropagation, where we were computing gradients of the loss function with respective of each of the parameters in the network, the weights and biases. We also discussed about a feed forward neural network. We took one case study of image classification using feed forward neural network. But then we show the limitations of feed forward neural network for the task of image classification, where we have dense connections. So we came up with the idea that we can have sparse connections, and the concept of weight sharing. And with the help of convolutional neural network, we will see how we can take advantage of these concepts of weight sharing and sparse connections, and implement the image classification, solve the image classification problem with the help of convolutional neural network. Fine. So we saw this, like how the deep neural network is more about representation learning, in contrast to traditional machine learning, where we used to extract features. We used to have handcrafted features. Here, the whole pipeline is about learning the rich features from the data itself, and then applying some kind of classifier. Coming to firstly, let's talk about the convolution operation. As you all are aware, convolution is nothing but element-wise multiplication and then aggregation of these multiplications. So here we can see this is the filter or the kernel, and this kernel is slided over all across the input image, and then we compute the aggregation. You can have an analogy from the feed forward neural network, where we had uh, pre computation of the pre-activation. So this you can correlate, or you can have a it is similar to what we did in feed forward neural network for computation of pre-activation. Here also we are multiplying the weights to individual inputs, and then performing the aggregation over it, and then further we will be passing this aggregation through an activation function. The only difference here is we are having the same kernel or the same weights which are being applied all across this image. In contrast to the feed forward neural network, where we had different weights for different connection. So that is how this convolution works. And these are few of the examples. Like this is a filter for the average filter, which basically blurs the image. Then this one is for sharpening the image. Further, we have edge detection filter. Some of the examples of edge detection filters are Kenny edge detector or the Sobel edge detector. So just a glimpse of convolution, how convolution works. What we can do is we can slide the kernel over the input image, and each time when the kernel is slide over this image, it computes one value of the output, and which is the next neuron in the next layer. So this is how one value, as a resultant of applying a kernel on the input patch, this is how it is computed. So the resulting output here, this matrix, is basically the feature map. So basically what exactly is going on here is uh, we are applying some kind of filter on the image, and this filter is responsible for extracting important information from this image, and this important information is nothing but a feature from the image. So that's why we are calling it a feature map. Now, not only a single kernel, we can use multiple kernels or the filters to extract different type of information from this image. In that case, we will have multiple feature maps as a result. Now, coming to 3D convolution, we can have a 3D filter. And how does this 3D filter looks like? You can see an example here. It's a 3D filter which is being applied on a 3D image. 3D corresponds to the RGB, red, gray, green, blue channels of the colored image. Now, we can apply a 3D convolution over this image. So basically, 3D convolution means this 3D filter will be convolved all across this image, and it will result into a 2D output. I'll tell you how. So basically, we will slide this 3D filter. The depth dimension is same. The depth dimension of the filter is same as of the input image. So basically, suppose there are three channels here. Here also in the filter we have three channels. Each channel in the filter is convolved with the corresponding channel in the image. So we are just sliding this kernel in width and height, not in the depth. That's why, as a resultant, we are getting a 2D output from these 3D convolution. You can see the depiction here. So in effect, we are basically doing a 2D convolution operation, on a 3D input, because the filter is only moving across the height and the width, but not along the depth. That's why we are getting a 2D output. And now we can apply multiple filters to get multiple feature maps. So as a result, this is a feature map of this image, which is being computed as a result of 3D convolution of the filter on this input colored image. Now there are certain issues while we perform convolution, and that is the issue is with the, I mean, there are issues on the edge side of the image. There are problems on the edges. So the solution is padding. We can add extra pixels on the image so that uh, we can apply the kernels on the edges itself. So there are different type of padding. One is like zero pad. We can pad 1 pixel on each side of this image, and that can preserve the shape of the image or the dimension of the image. If we don't do any kind of padding here, the output feature map dimension will be smaller than the input image. Next important term is stride. So whenever you are going to implement a convolutional neural network, these are the important terms or important factors in the convolutional neural network. Another one is after padding, we have stride, and stride basically tells you, it defines the interval at which the filter is applied over the input image. That means how many pixels I'm going to slide this filter in this direction or in this direction. So as the next convolution happens, how many pixels I have moved this filter in this direction. You can see here the stride was 2 because we have moved this filter by 2 pixels in this direction. So that's why the stride is 2. Now, why this parameter stride is very important, because the dimension of this output feature map will be governed by the stride value. More the value of stride, the dimension will be reduced further. Had it been stride is equal to 1, the feature map dimension will be larger. So basically, it means we are skipping every second pixel whenever we are moving this filter from one location to another location, and so on. That is how it works. So stride is same in horizontal and vertical direction. We cannot have different stride values for horizontal and then the vertical direction. So that is how stride is determined. Now, with With the understanding of padding and stride and convolution, we can calculate the size of the output feature map. So given with uh, given with input image of dimension w1 and h1, w1 and h1, and suppose the dimension of the filter is f cross f, and p tells you the padding and s tells you the stride, the dimension of the output feature map is given by this formula. W1 is the width of input image, H1 is the height of the input image, F is the size of the kernel. It can be 3 cross 3, 5 cross 5, 11 cross 11, and so on. And P is the padding, how many pixels we have added on the edges. And S is the stride, how many pixels we have skipped when the kernel is moved from one location to another. So this is the formula for computing the dimension of the output feature map. Now, it's obvious that the third dimension we are not considering, because I have told you when we apply 3D convolution, even then we are getting a feature map, 2D feature map, because we are not sliding the filter in the depth direction. Now, coming to the depth part, let me depict it again. As I told you, each 3D filter gives you a 2D output, because the dimension of this 3D filter, the depth direction of this 3D filter is equal to the depth of the input data, that is the image or any type of data. That's why you get a 2D output feature map as a result of 3D convolution. Now you can apply such multiple filters here. Suppose you are applying k number of 3D filters. Each filter will give you one 2D output. So if there are k number of filters, you will get k such 2D outputs. And now the formula will be like this one. The formula for the output dimension, width and height is same what we have discussed just before the slide. And the depth, output depth will be equal to the number of filters you have applied here. So that is about the depth. Now coming back to our discussion on classification using feed-forward neural network, try to recall our discussion where I depicted the image classification or digit classification using feed-forward neural network. Let's summarize that again and then compare it with the convolutional classification using convolutional neural network. What we do, suppose the image is of dimension 4 cross 4, we vectorize it, so it will be a 16 cross 1 vector, and these are nothing but the pixels, and it's an input layer of the neural network. Then at the output we have 10 neurons corresponding one each corresponding to one class. Since there are 10 digits 0 to 9, that's why we have 10 classes. In between we have hidden layers, and then suppose there are multiple hidden layers, then we have to compute these pre-activations and post-activations with the help of these input nodes, and there will be weights associated with each of these connections that we have already established yesterday, and then we have dense connections for each of the layer. This is regular feed forward neural network what we have seen earlier. There are many dense connections here, you can see, because each of the neuron in the previous layer is connected with all the neurons in the subsequent layer. And connection means we have weights and biases associated with that. So for example, all the 16 input neurons, these all 16 input neurons are contributing for the computation of H11 here. Similarly, all these 16 input neurons will help in computation of H here, and so on. So we have dense connections for each of the neuron. Now, in contrast to this feed-forward neural network, what happens in the case of convolution? That we have seen, and let's have a detailed discussion on this one. Again, we can have 16 pixels in this image because we have considered a 4 cross 4 image size, and then we are applying a 2 cross 2 filter over it and computing the output from this. Now what we are going to do here, for computation of H11, we will have the contribution of very few local neurons rather than contribution of all the 16 neurons which we had in feed forward neural network. Sorry. How? Because we are applying this 2 cross 2 kernel on a 2 cross 2 patch of this image. So only pixel number 1, 2, 5, and 6 are contributing for the computation of H11. Then for H12, the pixel number 3, 4, 7, and 8 are contributing for computation of H12. So firstly, we have very few local neurons that participate in the computation of these Hs. Secondly, there is a concept of there is a concept of weight sharing, because the same filter is being applied all across the image. That's a separate story if you want to use multiple filters, but the filter weights will remain same all across the image. So there is a concept of weight sharing. So firstly, we have sparse connections. We don't have dense connections, which has reduced the computation. We are taking advantage of the structure of the image. That means the interaction between the neighboring pixels are more interesting. The neighborhood are have similar kind of appearance. However, the pixels which are farther, they might be different from these ones. So basically, this sparse connectivity helps us in reducing the number of parameters in comparison with feed-forward neural network. Secondly, the concept of weight sharing. The filter which is being applied here, the same filter will be applied here. So here also we are saving, because let's say we are applying an edge detection filter. So that edge detection filter will be same all across the image. So that's the concept of weight sharing. I think this we have already covered. Now we can have multiple such kernels, different kernels, but whatever kernel we are using, it will have the same weights which will be applied all across the image. So that is how we are saving the number of parameters. This concept is called as weight sharing. So with discussion related to all the basic concepts of convolutional neural network, let's see how the convolutional neural network work. This was one of the first uh, convolutional neural network which was used for digit classification. We call it LeNet, and let's have a look on different type of layers in this convolutional neural network. This is the input image of dimension 32 cross 32. The first layer is convolution layer, which is responsible for applying filters to extract information from the image. So if we are applying filters, we can we can apply multiple filters in the convolution layer. So what happens here? You can see the parameters here. We have used stride as one. We have used five number of filters. Oh, sorry. We have used filters of dimension 5 cross 5. We can have s- six number of filters and padding as 0. With this, we can compute the number of parameters which are being used here, number of weights. How this 150 has come, let me tell you. 5 cross 5, that's that's 30. I think there is some mistake here. It should be 180 parameters because 30 is the weight number of weights in one filter, and then we are using six such filters. So that's why it will be 180 parameters in the first layer. Then next layer is pooling layer. We will talk about the pooling layer, what exactly is pooling layer in the subsequent slides. Next, we have the convolution layer 2. So as we go deeper into the network, whatever feature maps computed by the convolution layer 1, they are being passed through the pooling layer. Basically, pooling layer is responsible for reduction of the dimension of these feature maps. Further, they are passed through the convolution layer 2, which is also responsible for extracting more meaningful features. And further, it is being passed through the pooling layer. And then we have fully connected layers. And in the output, we have 10 neurons corresponding to each of the class. So it's an alternate convolution and pooling layer. Now we'll see these layers one by one. What is the role of these layers? So firstly, the convolution layer input is an image to the convolution layer. And what processing we do in the convolution layer, we apply multiple filters for extraction of the information. Output is a feature map, and the dimension of this feature map is derived from the number of filters you are applying here. Then the next layer comes is pooling layer, and the main task of this pooling layer is to shrink the dimension of the feature map computed with the help of convolution layer. So it pools pixel values over a region, let's say 2 cross 2 or 4 cross 4, and reduces the dimension. Here also we can see that what is the stride value, what is the padding value, what kind of pooling we are using, and most common dimensions of the kernel here is 2 cross 2 or 3 cross 3. It is used for dimensionality reduction. Also, one important thing to note here is there is an invariance to transformation of rotation and translation. We are preserving the spatial context of the image. We are not distorting the spatial context of the image. Let's see the depiction of pooling, how pooling works. Suppose this is 3D input, a 3D image or a RGB image. We apply a filter over it, a convolution filter, and we get this feature map. Now we are trying to implement or apply a max pool kind of pooling layer where the filter dimension is 2 cross 2 and stride is 2. Stride means how many pixels we are going to sift the filter. So the idea is we take these 2 cross 2 path size of the feature map, apply this 2 cross 2 filter. This is nothing but we are applying some kind of pooling operation on it. In the case of max pool, we find out the maximum value in this 2 cross 2 patch and propagate that further. That is how it works. So for first four values, a 2 cross 2 patch, if we are applying max pool, the maximum value will be put here. As a result, you can see that this 4 cross 4 feature map is converted into a 2 cross 2 feature map. So basically, we have reduced the dimension of this feature map with the help of max pooling or the pooling layer. Similarly, we can have another max pooling with a stride of 1. So of course, the dimension will be higher in comparison with this one where we have stride as 2 and so on. So instead of this max pooling, we can also have average pooling or min pooling based on the requirement of the model. Thirdly comes the rectified linear unit, the activation function. You have seen in the convolution layer that we have computed the convolution of the kernel with the image patch, and which is a linear kind of operation. With the help of this activation function, we are bringing nonlinearity into this operation, and basically you have seen the usage of activation basically helps uh, in activation of the subsequent neuron. So one of the popular activation function is rectified linear unit, which is being extensively used in deep neural networks. And this activation function is part of your convolution layer itself just after the convolution operation. So convolution operation is nothing but the aggregation, weighted aggregation, where we are convolving a filter with an image patch. So that's the aggregation. Now, rectified linear unit is an activation function which is applied just after the convolution operation. And the transfer function of this rectified linear unit is max of 0 and x. So basically it is linear in the positive range. However, it is 0 in the negative side. It looks like linear, but it is non-linear. That's why it is fast. uh, it learns fast and it avoids the vanishing gradient problem. So in rectified linear unit, we have a pixel by pixel operation that replaces all negative values by 0 and puts the same value for the positive ones. Here you can see for all these negative values are replaced with 0, and the positive values are propagated as it is. So that's the transfer function of rectified linear unit. Then finally, we have a fully connected layer. So let me go back to the slide where we were seeing all the layers. Yeah. So we do have convolution layer where we have 2D feature maps. In pooling layer also, we have two-dimensional feature maps and so on. But ultimately, finally, we have to bring uh, this feature map to a dimension of 10 cross 1, and which is a vector. So basically, this two-dimensional feature map has to be converted into a one-dimensional vector. And till this stage, we were maintaining the spatial context of the image. Now, with the help of this fully connected layer, we will convert or we will vectorize it into a single vector. So fully connected layer, the name fully connected means all these neurons are connected. The neurons of a layer are connected with each of the neuron from the previous layer. So the standard neural network, I mean, in the feed forward neural network, we had all of the layers as fully connected layer. So we are using similar kind of layers here because we want to bring that 2D feature map into a vector of neurons equal to number of classes. So uh, this basically used to go from the image feature map to the final output, and it also eliminates the spatial information. That is what I just told you. Now, this is again the example of digit classification. You can see here the digit image of a digit passed through different type of layers, the convolution layer and the pooling layer. So as I was telling you, LeNet was one of the first convolutional neural network for images, and it was applied on MNIST dataset by Lee Kun in 1998, and it yielded 99% accuracy. And it had convolution layer, max pooling layer, and fully connected layers. And it was trained through backpropagation algorithm. So this is how it worked. I mean, we were just discussing the dimension here, number of parameters. So the number of parameters are very less in comparison with the feed forward neural network. Now coming to the training part of CNN, if you can recall our discussion on training of the feed forward neural network, in the similar fashion we can train the convolutional neural network. In convolutional neural network, uh, we can do the training with the help of backpropagation algorithm in the similar fashion we did it for feed forward neural network. Let's see how. As you can see here in CNN, we have only few weights which are active. In the feed forward neural network, all these weights were active. However, in the case of CNN, only few of the weights are active. That means only some of the inputs are contributing to the edge in the next hidden layer. That means the rest of the weights, the rest of the weights which are depicted here in gray, they are zero. So we need not to compute the gradients of gradient of the loss function with respect to these weights because these are zero. So that has saved our computation for training these CNNs with the comparison to feed forward neural network. So basically what we can do is we can train a convolutional neural network through back propagation, and considering it a feed forward neural network which has very limited number of weights active, rest of the weights are zero. So we will be computing the gradients with respect to the active weights only, and since the rest of the weights are zero, we need not to compute the gradients, and that is how the training will happen for CNN. So that completes our discussion on the fundamentals of deep learning. Let me quickly summarize what we have talked yesterday and today, starting from the history of neurons inspired from brain, and then slowly simple computational models were developed where only Boolean numbers were taken as input, the MP neuron, and the thresholds were hard coded. The idea came into mind that why can't we have weights associated with different inputs? Why can't we give more importance to a particular input? So the concept of weights came into existence. So instead of having simple aggregation of the input information, we have weighted aggregation of information in the perceptrons. And also there came a concept of bias where we are taking that threshold as one of the weight for the neurons. Further, since these thresholding based mechanisms were harsh, so there came a concept of sigmoid based thresholding or activation. So the concept of activation came into existence with the help of sigmoid functions. And further, we talked about one layer neural network, then feed forward neural network. We took some examples related to image classification using feed forward neural network, where I depicted that what is the role of hidden layer, and how these hidden layers are responsible for extracting information from the input data, and only the relevant neurons are activated. As a result, in the output layer only a particular neuron will be activated. That means it will be having the highest probability in comparison with other output neurons. That signifies classification to a particular class. And then we take up the discussion on deep neural networks. We talked about representation learning. We compared deep learning with traditional machine learning. Traditional machine learning is more about feature engineering, extracting features from the image and then applying some kind of classifier. However, the deep neural network or deep learning is related to representation learning. Uh, the main idea behind deep learning is to learn features from the data itself rather than computing handcrafted features. So that has helped in improving the performance of these models. Then we talked about one of the popular model of deep learning, that is convolutional neural network, which has shown promising results in the field of uh, in every field, rather it is computer vision or NLP or any other field. We talked about convolutional neural network, different layers of convolutional neural network. We shifted from feed forward neural network to convolutional neural network, where we have sparse connections and have a concept of weight sharing, which tremendously reduced the number of parameters to be trained. And we discussed different layers of convolutional neural network. The convolution layer, the pooling layer is responsible for dimensionality reduction, max pooling, average pooling, min pooling. Then we talked about rectified linear unit, and then as we can have combinations of convolution, pooling, and fully connected layer in convolutional neural network. And we also discussed about in the last we discussed about the training of the CNN. We can train the CNN in the similar fashion we train a feed forward neural network using backpropagation algorithm. Here, the difference is we have only sparse connection, only few weights are active, others are zero. So we need to compute less number of gradients for backpropagation algorithm. So that completes the discussion on fundamentals of deep learning. Next, we are uh, going to discuss the practical implementation of the convolutional neural network. So for that, we are going to use Google Colab. So before proceeding ahead, I think we can have just a quick break of 5 minutes, and then we will continue. We'll spend one more hour on practical implementation of CNN. So I'm just muting myself for next 5 minutes. Uh, right now it's 14:44. Let's meet at 14:50 or 14:49, and then we will start uh, the practical implementation on Google Colab. So meantime, I request all of you to please keep your Google account handy. You can open Google Colab, and then I'll demonstrate you how you can use Google Colab for implementation of any model. Yeah, so welcome back. I think we can start the next session, which is practical hands-on implementation of convolutional neural network for image classification. So I request all of you to please open Google Colab. Let me share my screen and then demonstrate you how we can open Google Colab. So I'll just write Colab in the Google. So it's collab.research.google.com. You can open it and log in it with the respective Google account in which you want to write this program. And here, what you can do is on the bottom side, you can see there's a tab for new notebook. You can click on it, which will create a new notebook for the experimentation. Now you can see here, you can give a title to it. It's untitled as of now. You can give a title to it. The title may be Hands on CNN. Right? So I have given a name to this uh, file, this notebook. Now here there is an option to write the code. So firstly, I'll import the libraries. I request all of you to please open the Google Colab and start writing the code along with me. I'll have a very less speed for writing the code and executing it. If you still face any difficulty, please write the issue on the chat box so that I can help you in implementing that. So I hope everybody has started the Google Colab and created a new notebook. Fine. So firstly, we will import some important libraries like import OS. Next, I'm going to import TensorFlow. We will be implementing this CNN model using TensorFlow. So import TensorFlow as TF. Then for plotting or displaying the images, we will be using matplotlib. So just import matplotlib dot pyplot as plt, and then we can use the numpy. So we will import numpy. Numpy is a library for numerical calculations. So import numpy as np. What we have done, we have imported all the libraries which we will be requiring in implementation of this CNN model. So here you can see an arrow. You can press it, so it will run this particular cell. The Google Colab provides you the facility to have blocks of different codes. So you can have different code blocks and execute them one by one. So you can see here there is an error and there was a typo error. It was matplotlib, not marplotlib. So let's run it again. And this shows that this has the all libraries are imported. Now next, what we are going to do is we will use a MNIST dataset. We will implement this CNN. Uh, we will implement this CNN on MNIST dataset, the digit classification dataset, which we have seen in the theoretical discussion. So firstly, let us load the dataset. It's always good to write comments and in the code so that others can also understand what you have written in the code. So load and pre-process the MNIST dataset. And for writing commands, you can use this hash at the start of this. So the first step is load and pre-process the MNIST dataset. So how you are going to load it? So before that, I just want to tell you that the dataset has majorly two parts. One is the training part, the data which will be used, and the images in this case, which will be used for training the model. And then there is test dataset, which will be used to test the developed model. Apart from that, from the training data itself, some of the portion is being used for the validation of the data, validation of the training, validation of the training of the model. So that is part of your training data itself. So for that, I'll pick X train and Y underscore train. So X train basically stores the input images. Y train is the corresponding labels. Then similarly, we can have X test, the test images, and the corresponding labels. And we will download it from the Keras dataset. So tf.keras.dataset. You can see here we also get suggestions directly. You can use these suggestions. So Keras provides different kind of data sets, and you can see the examples here like California housing dataset, CFAR 10, CFAR 100, Fashion MNIST, IMDb, MNIST, Tutor, and so on. So we are interested here in MNIST, and from MNIST, we will use a function called load data. You can see here it is giving you a suggestion, load underscore data. Right. So what we have done here, we have used the already existing data set being provided by uh, TensorFlow, and we are downloading that data in the format of training and test data set. So this line basically gives us, downloads the data and bifurcates them in train and test set. I hope everybody is on same page. Let me check if any comment is there on the chat box. I think no. Fine. So that I'm assuming that everybody is progressing well on this implementation. Next, what we are going to do is we are going to normalize this data set. So I'll normalize these images, the input images, X train and X test. Normalize means we are normalizing the pixel values with 255. So X train divide by 255.0 and X test divide by 255.0, and this is nothing but normalized pixel values. As a result of this normalizing, the range of pixel values is from 0 to 1. Then the dimension of this data set is 60,000 cross 28 cross 28. Now since it's a grayscale image, we want to convert it into not convert it into, we want to consider one channel, because usually we have three-dimensional images RGB which has three channels, but since it's only one channel because it is grayscale, so we will add that fourth dimension which signifies the channel number. So it will be the first channel of it. So we are adding the fourth dimension here. That is how we are going to add it. Let me tell you. Xtrain is equal to X train, and these are all the earlier dimension, and we are adding a new axis to it. So new axis, which is the fourth dimension. And so there are three dimensions, and further we are adding the fourth dimension. Similarly, we'll do the same operation to the test data set. Right. So till now, what we have done, we have downloaded the data, normalized the data, and then add fourth dimension signifying the channel. So let me run it. So this, you can see it has started downloading the data from this website. And once this has downloaded, let's see what is the dimension of this data set. So I'll x underscore train dot shape. So see what exactly we have done here. Earlier the dimension was, there are 60,000 images of 28 cross 28 each, and with the help of this particular command we have added a new dimension to it. Similarly, we do have uh, dimension of test data. So let's see what is the dimension of the test data. So here we have considered 10,000 images each of 28 cross 28, and here we also added a new dimension, the channel dimension here. Now, given the data set, now next job is to create the CNN model. So the next step is the second step, create the CNN model. And how do we create that? So for that we write model, and model will be equal to, so this is a variable, you can write anything, you can write CNN underscore model or CNN or model or anything you want to specify. So basically we will be adding layers to this model, the convolution layer, pooling layer, or uh, the fully connected layer, or also the dense layers. We also call them as dense layers. So let us do that. So tf dot keras dot sequential. Sequential means these layers are added in sequential manner. Sequential, and right. Now we'll add one layer at a time. Just give me a moment. It is auto-filling it. Let me correct it. Fine. Now let us add one layer at a time. Tf dot keras dot layers, and first layer will be convolution layer. It will be a 2D convolution, since the image we are considering here is grayscale image. So it will be a 2D convolution. Had it been RGB image, it could have been a 3D convolution. And what all parameters we are passing on here, please note carefully. We will pass on the input dimension, then we will have the filter size 3 cross 3, then we will define the type of activation. Remember, I told you that the rectified linear unit is applied just after the convolution operation. So I'll define the activation type, which is ReLU, and then we have input underscore shape, which is, you are aware that it's an image of 28 cross 28 cross 1, because it's a grayscale image, so there is one channel. Remember, we downloaded 60,000 for training, 60,000 training images and 10,000 test images of dimension 28 cross 28 each. Then next we are going to uh, add a pooling layer, tf.keras. Here this 32 is basically the number of filters we are going to implement here. 32 filters of dimension 3 cross 3, and the input shape of the image is 28 cross 28 cross 1. So tf.keras.layers, and this time we are using max pooling, and it will be 2D max pooling. It's single L max pooling, and here, since it's max pooling, we are using a 2 cross 2 filter size. Again, next we are going to use a convolution layer, layers dot 2D convolution 2D, and remember what all parameters we have to pass on here. This time we are using 64 filters, each of dimension 3 cross 3, and we do have uh, activation as ReLU, and we need not to define the input shape here because it is a hidden layer. We defined the size, input size here, because it was the input layer where we were inputting the image itself. Here it is in sequence, so whatever output this particular max pooling layer will give, that will be the input to this convolution layer. Next we are again going to implement a pooling layer, add a pooling layer. So tf.keras.layers dot max pooling 2D, and the dimension is 2 cross 2, 2 comma 2, and then we'll use a flatten layer to flatten this feature map, this two-dimensional feature map. So tf.keras dot layers dot flatten. Flatten means this output is two-dimensional here. We will vectorize it and make it single dimensional. And then we will be using the dense layers. Layers means the fully connected layer, where each of the neuron is connected to each neuron in the previous layer. So tf dot keras dot layers dot dense, and see what parameters we are passing on here. Uh, Number of nodes and activation. Again, we are using ReLU, rectified linear unit, and we are naming. We can name this layer as, since these are features, so we can name it as features. You can name it anything. You can name it as first dense layer, or first fully connected layer, or features, whatever you want to name it. Next is, again we will have a dense layer which will have 10 neurons. So keras dot layers dot dense, and this time we will have 10 neurons because we are having 10 classes corresponding to each digit. And try to note here that we are going to use softmax activation function. So why we are using softmax activation function here instead of ReLU? Because this is the last layer where we have to compute the probability for each of the class. So this softmax is basically giving us the probability corresponding to each of the class. So that's why we are using softmax as activation function in this last layer. So that basically completes the implementation of the CNN model. So we have created a CNN model which have two convolution layer, two max pooling layer, and two dense layers. Let's run it. Let's see if it is correct. I think it is giving us some error. It says that TF Keras layers has no attribute max polling. So there is a typo here. It will be POOLING. Again, here it is POOLING. Max pooling. I can run it again. Yeah, so there is no error. That means it has successfully run. Meantime, let me check if any query is there. Can we do it on Jupyter? Yes, you can do it Jupyter as well. I mean, you will have to install certain dependencies. Might be on your computer, you might not be having TensorFlow installed or other libraries installed. So in that case, you will have to install these libraries. Definitely, you can do it on Jupyter. So let's continue. Next step is to compile this model and see what is the model summary. So the third step is compile the model. And so basically, model we have already created. The name of the model is MODEL model. You can use compile, model compile. And here basically we tell the model that what uh, loss we will be using, what metric we will be using, and what type of optimizer we will be using for training. So let's define optimizer. Optimizer is Adam. Then what kind of loss? So basically, usually we consider uh, cross entropy as the loss function, cross entropy. So for classification kind of problems, we always use cross entropy loss. And the metric which the model will use during the training, so its accuracy. You can define any other metrics as well. This is metrics basically. You can have more than one matrix as well. So let's compile it, and in the last, let's plot or let's display the model summary. It will tell you what all layers are there. So let me run it. You can see here uh, we used one convolution layer, the first convolution layer, which is the output shape of that feature map from this convolution layer is this one. And these are the number of parameters. Try to recall what we had here. 3 cross 3 filter, 32 such filters, and input dimension is this one. Try to recall the formula. W2 is equal to W1, and the formula was dependent on the stride and the padding. So W1 plus F plus 2P divided by S. Sorry, W1 minus F plus 2P divided by S plus 1. So with that formula, we get this output dimension, and try to remember the discussion related to the depth. So the depth of the output feature map is equal to the number of filters we are using. Since we have used 32 filters here, the depth will be 32. Then max pooling, so it is 2 cross 2. So this 26 cross 26 is transformed into 13 cross 13. Then again we have convolution layer and max pooling layer, and then flatten layer, features. And since we gave it a name as features, that's why it is showing as features. And try to see the number of parameters we have. So basically, there are total this much parameters which are trainable parameters. Now, the next step is to train the model. So that is very simple. You have to just write the train model.fit. So fourth step is train the model. Train the model, and we have to just write model.fit. Here we have to pass on the training data set. So the training images, set of the training images and the corresponding labels. So x underscore train, comma y underscore train, which is the label. And we need to define how many epochs we want to run. Epoch one epoch is once the whole training data set is passed for training, that is one epoch. So for uh, faster computation here, we can use a smaller number of epochs. So let's say we are considering 3 epochs. You can train it for more number of epochs. The more the number of epochs, uh, slowly it will increase the accuracy and reduce the loss. And basically, we can plot this training curve, the loss and accuracy curve, and then we can decide where to stop this training process. So epoch is equal to 3, and we will define, as I was telling you, the validation data set. Validation data set is part of your training data set itself. So we need to define what will be the split of validation. So suppose we are considering 10% split. So 10% of the training images will be used as validation during the training itself. So validation is basically is validation data set is basically used for uh, keeping a checkpoint on the training, whether the training is being done correctly or not. So whatever model is trained in one epoch, that is tested on the validation data set, and then accordingly the parameters are changed. So let's run it. I think there is some error here. Tells us model.fit. Yeah. So there is a typo mistake here. We have to write epochs. Then again, there is some mistake in this validation underscore split. Spelling is wrong. Is split. Now you can see it has started training, and during the training, it is telling you what is the accuracy and what is the loss. So basically, the aim of the training is to increase the accuracy and decrease the loss. So it is during this training, it is adjusting those weights and biases so that the accuracy increases and the loss is minimized. So let's wait for the completion of the training. This is the third epoch. You can see the accuracy has increased in the second epoch. loss has tremendously reduced. And finally, in the third epoch, you can see the accuracy is increasing and loss is decreasing. So that completes the training. We can increase the number of epochs here, but just we do have time scarcity, so I just consider three epochs. You can train it for more number of epochs. Now, next is once the model is trained, now we can test it. So the next step is to evaluate the performance. The fifth step, evaluate the model on the test set. Try to recall, when we downloaded the data set, it was divided into training and testing. The training data set was provided in the upper step here, where we were training the model. Now we will use the test set x underscore test for evaluating the performance. So let us see how the model behaves. So test underscore loss. This accuracy during the training is for the training part and validation part. Let's see how it behaves on the unseen data, which is the test data. So test loss and test accuracy is equal to model dot evaluate. So evaluate model dot evaluate, and we will pass the test data and the test labels, and then let's see how it behaves. And we will print the test accuracy slash n test accuracy is now let's run it. So it will test the model on those 10,000 images and tell us what accuracy this model has achieved. So let me run it. So this model has got 98.71% accuracy on the test dataset. Now the next step is to just visualize the results. We will visualize the results, like for a particular image, how that image looks and what was the model result. So for that, I'll write a code. I hope there is no query as of now. What is the purpose of epoch? Fine. So purpose of epoch is uh, how many times the whole training data set will be passed to the model for training. As we, during the training, we pass the training data set multiple times, and in every iteration, we try to reduce the loss and update the weight parameters. So, for more, we can have more number of epochs for training the model. So it's a trade-off. So basically, whenever we are training the model, we plot the accuracy and the loss values. And at a certain point of time, the loss becomes stable, the accuracy becomes stable. So that is the optimum number of epochs for which we should train this model. Someone is saying, I can't see your screen. I hope everybody is seeing the screen. You can. I have already shared the screen to all of you. Please let me know if still you are not seeing the screen. Okay, fine. So, okay, so next let's move ahead and let's see the results on individual images. So next step is predict and visualize. So we'll see visualize the image. So for that, we are going to make a small function. Uh, yeah. So let's write the predictions. What all predictions are there? Predictions is equal to model dot predict, and we are passing the whole x test to this model dot predict. Let's see what result we get. So we have what we have done here is in this predictions variable we have stored the prediction on each of the image available in the X test dataset. So this prediction is basically, see the dimension here. Prediction has a dimension 10,000 cross 10. 10 corresponds to each class. So what is the probability of all those 10 classes corresponding to one image? So that is predictions. Now, once we have stored the results in these predictions, now we will try to visualize it. Let's visual. Firstly, let's write a visualization function. And for that, I'm just writing a small function called plot image, and then I'll call this function afterwards. So plot image, and inside this plot image as an argument, I'll be passing the index of the image in X test set, and I'm also passing prediction underscore array, the prediction which we have done, and we are passing the true label which was available during I mean we have downloaded those true labels from the dataset. So true underscore label, and then I'll pass the image. So what I'm trying to do here is I'm writing a function named as plot image. As an argument, I'll pass on the image, the true label of it, the actual prediction, and the index of that image in that array. In that array. So firstly, what I'm doing is I'm just trying to have uh, just a minute. Um, Indentation is need to be done. So true underscore label, and the image we can fill from true underscore label ith index which we have passed, and img I dot reshape. We are basically reshaping it back to 28 cross 28 because it was in 28 cross 28 cross 1. Remember, we added a new dimension to it, and then we can define whether we want to have grid. So grid in the plot, we can make it false. By default it is on. Then plot x ticks, so x ticks, yes, we will have x ticks. Similarly, we can have y ticks, and then we will use imshow. So plt dot imshow, and as an argument I'll be passing that image. So what we have done in this step, we have extracted from this set the ith index from this set. So ith index is extracted, the true label of ith index and the corresponding image is extracted, and then we are displaying the image. Along with that, we are also binary, and then we will say that what is the predicted label and what is the actual label. So predicted label will be passed on in this particular array. So at ith index, I'll be taking out. So predicted underscore label is equal to np dot arg max prediction underscore array. So basically, what we have done here, we have passed on a prediction array. Uh, this prediction array is nothing but it contains 10 values, and out of those 10 values, whichever index has the highest probability, that will be the predicted label. So that is how we have computed the predicted label. Also, we need to have true label. So before that, let me define the colors. I want to have color as blue. If predicted underscore label is equal to true label, else it will be red. So during the display, if the predicted and the actual uh, true label matches, then the color will be blue, otherwise it will be red. Fine. And then we'll define the label. So what x label, we will, what all we are going to print in the x label. So this will be a string, and so we will print predicted underscore label. Then next we are going to have the prediction array. So it will be percentage. The probability will be displayed in terms of percentage. So 100 np dot max, and the prediction array, prediction underscore array. So what we are doing, we are finding the max value from this prediction array and displaying it as percentage uh, by multiplying it with 100, and array, and then we can one decimal and percentage, and then we can have display the true label. The true, it's little complicated, but if you continuously do it, it's easy to recall. So true label, I have to take care of these brackets as well. I think yes, and that is fine. And of course, we will define the color which we just now mentioned. It will be blue if it matches, the prediction matches, and it will be red if it doesn't match. So what we have done, we have defined a plot image function which we will be using now. Inside this plot image, we have set all the parameters for the display, like the x label, and we have shown the image, and we have uh, put false for the grid, and so on. So let's run it first. I hope there won't be any error. Yes, there is error because for function we use the column here. Fine. Now we are going to use this function to plot. The, the eighth step is the eighth step is plot first 15 test images with predictions. So we have already implemented the function. It is just to call that function. So plt dot figure, we will define the subplot size, what will be the dimension of this plot. So the fig size will be fig size is equal to 10 5, and then for we'll run a for loop for in range 15 I in range 15. We plot them one by one. Plt dot subplot. I think those who have used MATLAB, they can easily understand it. Plt dot subplot, and in that we are passing 3 cross 5, and every time I'll be passing I plus 1. So starting from first image, we'll be having 15, and the subplot is 3 cross 5. And then let's call that function which we have just written here, plot.image, and inside that pass on the relevant arguments. So plot underscore image, and here I can see I is the index of that image, then predictions corresponding to that ith index. So it will be a vector of 10, because it will tell you the probability of all those 10 classes, and whichever class has the highest probability, that will be the class of this image. And apart from that, we will pass the true label y test, and we will pass the set of the image as well. If you can recall this particular function, what we have done, we have passed the true labels, the set of true labels, set of images. Out of this sets, what we have done, we have extracted the true label from ith index and the image from the ith index from this set. So it is predictions. So predictions ith index we are passing on here, and then we can have plot a tight layout. It should not be, I mean, there should not be any spaces. Okay. Layout, and then show plt dot show. Let's see how it works. So what we have done, we have just we are trying to plot initial 15 images and see what is the true label and what is the predicted label, and with what probability the model has detected it. Let's run it. Yeah, fine. So this is digit 7. Now try to recall what X label is here. First one is predicted label. So this is predicted label 7. Next, we are displaying the probability for this particular class in percentage with one decimal point. So that is 100.0 percentage. Next, we are displaying the true label. Let me run it again. Yeah. So what is the true label which was there in the data set? It is 7. So that's why it is 100% probability. Second one is predicted is 2 with 100%, and true label is 2, and so on. You can see all of them are predicted correctly because we are displaying them in blue. And try to recall, if the predicted label is not equal to true label, it will be shown in red. So I think that completes the practical implementation of the CNN for image classification. Now, let me take the questions. Backpropagation is used in epoch to reduce the error. So basically, let me show you. Wherever we were training the model, I mean, the TensorFlow itself gives us the facility to for training. We just need to define what is the training data set, how many epochs we want to run, what will be the validation split. We need not to implement those back propagation algorithm, because those are already implemented by TensorFlow in the background. We are just importing the TensorFlow library and using the relevant function for training. In the background, the library basically does all those calculations and train them. Any other question?
Participants, we are open for the questions. If you have, then you can type at the chat box. So it seems that currently, sir, there is no question.
All right, sir. Then I think we can conclude here.
Yes. So anyhow, sir will be joining with us on Monday as well. Okay. So if you have any further doubt, then definitely means you can ask sir on Monday. So thank you, sir. Thank you, sir, for spending time with us. Can you share the code so that we
Yes,
have to? Yeah.
yes, definitely we'll share the code with you.
Yeah, yeah. So, sir, code and PPT, if you can
Ha. I'll
send
share
it to
code
me,
and PPT.
then I will do it. Okay. So, participants, I have uploaded all the video lecture before this lecture. Okay. So, I will just upload that also. So, definitely means you have all the video lecture and the materials. Possibly, I am asking for a few expert, but whatever the PPTs I received from the expert, that I have already uploaded on a means a canvas platform. Okay, so that's all. And still we have a session at 4 to 5 today. Okay, so be with us. Okay, because there is a last session is there where Gitanjali will actually explain you how you can process the EEG signal. Okay, but before that there are few announcements that tomorrow at morning 10 a.m. to night 10 p.m. the quiz will be open for a 15 minutes. There will be 20 questions and 15 minutes will be there. So that you need to attempt at Canvas. Okay. So tomorrow there will be quiz from morning 10 to 10 p.m. at the night, but you need to spend only 15 minutes. Okay, out of this 12-hour schedule. So that is what means is announcement. And again, we can take a 15-minute break. So please do join us at 3:57, 3:58. So we can start the session at sharp 4 o'clock. So see you at 4 o'clock again. Okay, thank you.